Any valve can be turned into a control valve simply by adding an actuator. Valve actuators, in response to a signal, move a valve to a desired position using an outside power source. These outside power sources may be in the form of pneumatics, electronics, or hydraulics. Pneumatic actuators move a valve's position by converting air pressure into linear or rotary motion. Linear motion devices open and close valves such as gate, globe, diaphragm, and others with a sliding stem to control the position of the flow control element. Rotary motion typically operates quarter-turn type valves such as ball, plug, and butterfly. A quarter-turn valve is one which can be opened 100% by turning the flow control element just 90 degrees. There are three types of pneumatic actuators: diaphragm, piston, and vane.
Control valve actuators control fluid in a pipe by varying the orifice size through which the fluid flows. Control valves contain two major components, the valve body and the valve actuator. The valve body provides the fluid connections and a movable restrictor comprised of a valve stem and plug that is in contact with the fluid that varies the flow. The valve actuator is the component that physically moves the restrictor to vary the fluid flow. Three actuator types are used in control valves, and they include spring and diaphragm, solenoid, and motor. As the name suggests, the spring and diaphragm actuator uses a spring and a diaphragm to move the valve stem and plug. A 15 psi pneumatic signal enters the housing at the top of the actuator. As pressure is exerted on the diaphragm, a downward force is applied against the spring, which moves the restrictor. The diaphragm moves until it creates an equal but opposing force against the spring, at which time the motion stops as the plug meets the valve seat. With no air pressure, the restrictor is pushed upward by the spring to act as a normally open control valve. To vary the position of the restrictor and flow through the valve, a current-to-pressure transducer can be used to provide a 3 to 15 psi signal to the diaphragm. At 3 psi, the valve is maintained open, and at 15 psi, the valve is maintained closed. Pressures between the 3 to 15 psi range proportionally change the flow of the valve. For example, a pressure of 9 psi applied to the diaphragm moves the spring and valve stem to 50% of operating range. For on-off control of the valve, a solenoid is used to actuate the valve to a fully closed or fully open position. Applying current to the coil generates a magnetic field that moves the plunger downward against the return spring. With zero current applied to the coil, the spring pulls the plunger upwards to the fully open position for a normally open state control valve. Another method for variable valve positioning uses a motor and is referred to as proportional control mode. Using a gear motor attached to the valve stem, a servo amplifier provides a DC control signal that moves the valve to the desired position. Feedback is achieved with a wiper arm attached to the valve stem that sends a signal back to the servo amplifier where the position is monitored. The servo amplifier drives the motor until the control signal is equal to the feedback signal.
Million possible combinations. When you're creating an application, it pays to understand how check valves work. Here are the important things to know. First, a check valve's components are in contact with each other all the time, even before gas or liquid flows through it. Any valve that's inactive for a long time can be susceptible to leaking or stiction, where the O-ring has a delayed separation from the seat. When a valve contacts liquid or gas, certain chemicals can cause O-rings to expand, and any debris in contact with the O-ring can keep it from seating properly. As the valve starts opening, a small amount of flow escapes. Is that amount minor or significant? Knowing this helps us pair the right spring pressure with the right O-ring. Once pressure builds, the O-ring lifts off and there's significant flow. We are now able to assign the opening pressure, one that exactly suits your application design criteria. With the valve fully open, the poppet travels to its limit. To raise flow beyond this takes a large increase in pressure. It's always good to order a valve with sufficient flow for your operating pressures. Now pressure decreases, and the components begin to move back. Reseal pressure is around 20% lower than the opening pressure. Finally, the spring force compresses the O-ring enough to hold it in place. The valve reseals and resets, ready to repeat the process.
The pressure relief valve is one of the most important types of safety valves. This type of valve sets a limit on the rise of pressure within a hydraulic line. In normal operations, the valve is closed and no fluid passes through. But if the pressure in the line exceeds the limit, the valve opens to relieve the pressure. This protects expensive machinery such as motors, pumps, and actuators from becoming damaged from high pressure. Without a relief valve, pressure can continue to grow until another component fails and pressure is released. Pressure relief valves fall into two categories: direct acting or pilot operated. A direct acting relief valve is held closed by the direct force of a mechanical spring. The spring force holding the valve closed is opposed by the system hydraulic pressure. The cracking pressure is the minimum pressure at which the valve will begin to open. This pressure is set by changing the tension in the spring using an adjusting nut or knob. As long as the system operates at a pressure at or under the cracking pressure, the valve remains closed. If the hydraulic pressure increases even a small amount beyond this level, the valve begins to open and fluid begins to trickle through. The pressure at which the valve is fully open is called the full relief valve pressure and is higher than the cracking pressure. When the hydraulic fluid in the system reaches the full relief valve pressure, the valve will be fully open and all fluid is discharged through the outlet port. A pilot-operated relief valve makes it possible to handle higher pressures and flow. It's also much smaller than direct-acting valves rated for the same pressure. This valve has two stages. The first stage is composed of the main valve with a poppet and spring large enough to handle the maximum flow rating of the valve. The second stage is composed of a much smaller direct-acting pilot valve, which includes a pilot relief poppet, pilot spring, and an adjustment knob. This smaller relief valve is usually mounted crosswise on the main valve body. As long as pump line pressure is less than the relieving pressure set on the control knob, the pilot poppet will remain closed. Since the pilot poppet is closed, the pressure in the main spring chamber is the same as the line pressure. Since these pressures are equal, there is no pressure drop from one side to the other, and the main poppet also remains closed. When line pressure increases higher than the relieving pressure, the pilot relief valve moves to its open position. This allows fluid to flow from the pressure side through the orifice and across the pilot relief valve to the tank. Once the pilot valve is open, there is now a pressure drop across the main valve poppet with a higher pressure on the pump line side. This causes the main poppet to move, allowing full flow through the relief valve. The same is true in reverse. As the pump line pressure decreases below the relief pressure set by the adjustment knob, the pilot valve will close. This allows the main spool to close and restores a balance of pressure. Relief valves can be used anywhere in a hydraulic circuit where it's necessary to prevent pressure from exceeding a maximum level. Advantages of direct-acting valves are their low cost and fast response times to pressure spikes. Pilot-operated relief valves are advantageous due to their smaller size and ability to work with higher system pressures and higher flows.